All right, well, good morning and good afternoon to those of you out on the East Coast. Thank you guys for joining us. This is the closeout presentation for the West Virginia Eco Forecasting 2019 Summer Develop project. My name is John D'Alessandro. I was the project lead, and I'm joined with my team members, Mason Bull, Tia Francis, and Katie Yutt. And we're just going to give you a little preview and kind of summary of our project this summer, which was all about forecasting red spruce restoration within the Monongahela National Forest. We're part of the DEVELOP program, like I mentioned, and DEVELOP is part of the Applied Sciences program within NASA, basically with the mission of using interdisciplinary research, looking through the lens of these things called Earth observing satellites that basically will help to solve environmental issues. Basically, this builds capacity between us, which are the DEVELOP participants, and you all, which are our partners. And before I do get started, since you guys are all end users, collaborators, and project partners, if at any point during the presentation, if you need something to be clarified or you have a question, please don't hesitate to speak up and we can try and give a better response or maybe clear things up. We are recording this presentation. I just wanted to let everyone know that. So let's get started.
It is made by.
Nope. Can you click it?
Yeah, I'll click it.
Cool.
Cool.
Give her a click.
What is going on here? There we go.
Anyway, so as I mentioned, we're forecasting red spruce restoration in the Monongahela National Forest, and I know that's a lot of you guys' backyard, so you guys probably know it very well. But it's located in the Allegheny Highlands of West Virginia. It's almost 7,000 square kilometers in area, and it ranges in elevation between 300 and almost 1,500 meters above sea level. It's a mesic environment compared to the xeric environment that we have out here in the West. So a lot more of a wetter type of climate. And I mentioned we're using these Earth observing satellites. In particular, we used Landsat 5 and Landsat 8. And the Monongahela National Forest actually falls into Path 17, rows 33 and 34 of these Landsat satellites. As kind of a case study and a little bit more of a local type of analysis, we also looked at the Sharps Knob restoration area. This area is about 50 square kilometers, about 1,400 meters above sea level. Great candidate for red spruce restoration. There's already been some activity there. And that's going to kind of be more of a local look.
All right, so I'm sure the majority of everyone on this call is very well aware of sort of the background behind the study site that we're looking at, but the project background is really what's driving our project forward. So we really still wanted to talk about those sort of main events that happened that are really, they're essentially why we're doing what we're doing in this project. So first, in the 1800s, a lot of the forests in the Monongahela National Forest were dominated by red spruce canopies. Then following a period of extensive mining, logging, and some very heavy wildfire seasons in that late 19th century and early 20th century, we had a widespread transition from that red spruce canopy to non-native hardwoods. During this period, in 1920, part of this area was established as the Monongahela National Forest. Then in 1989 and the late 1980s, the Monongahela actually purchased a lot of former strip mines, and Sharps Knob is actually included in these former strip mines that we're talking about. Now, considering this transition from red spruce to non-native hardwoods, the National Forest saw a very critical need to begin to restore red spruce to its historical extent, and in May of 2018, the Sharps Knob Red Spruce Restoration Initiative was launched. And because of this transition, there's a lot of community concerns and reasons why the National Forest is so concerned with restoring red spruce. And these are sort of the really big reasons that we chose, or we're focusing on this project. These are the things that are driving this project forward. First of all, biodiversity. Red spruce provides shelter and food for two of the Monongahela National Forest endangered species, which include the cheap mountain salamander and the northern flying squirrel. So from that, you can see restoring red spruce to its historical extent is very important for the survival of these two species. In addition, red spruce are associated with a sort of special type of soils. They tend to be absorbent and have a higher hydrologic capacity when compared to non-native hardwoods. And these properties, these hydrologic properties, are very important implications for water quality and flood management within the region. In fact, the Forest to Faucet program that is run by the USFS actually categorizes the watersheds that are within the Monongahela National Forest as being very critical for drinking water, particularly drinking water for the city of Pittsburgh. And in addition to these very critical hydrologic soil properties, the soils that are again associated with red spruce also have important implication for soil organic carbon stocks and for carbon sequestering. In fact, current research actually estimates that 6.6 teragrams of carbon could be reintroduced into the soil from the atmosphere just by restoring red spruce to its historical extent in West Virginia alone.
So now I'd like to mention the partners a little bit. Obviously, some of our partners are on this call, so you know who you are. But for anyone who doesn't know, we were partnered with the United States Forest Service, as well as NIACS, or the Northern Institute of Applied Climate Sciences. And we really, they were a big help. They gave us a lot of help with this project, data, just direction to go. The people on the slide, we'd like to thank especially. You guys helped out a ton. We really appreciate all of your help, and the project wouldn't have happened without you guys, so thanks a lot. And now I can talk about our objectives a little bit with this project. So chiefly, the project objective was to identify the historical extent of red spruce between 1989 and 2018. And after we got this classification of identifying this red spruce, the idea was to create maps of these red spruce localities, and then all of the suitable locations within Sharps Knob and the Monongahela as a whole to figure out where we can go back and plant. And then another thing we wanted to do with this was forecast out to 2040 all of the land cover for the Monongahela National Forest. And then finally, we had a lot of great data, great results, and so we wanted to be able to reproduce this with the partners. And so we created a tutorial of our specific workflow for our partners to be able to reproduce these processes at any scale and any time of their choosing.
So with all those objectives, we kind of had a really great opportunity to work with like the backbone of our project, which is these NASA Earth observing satellites that I talked about earlier. In particular, the all-stars of this were Landsat 5 Thematic Mapper and Landsat 8 Operational Land Imager. Landsat 5 was used for our 3 earlier dates of imagery of 1989, 2001, and 2007, where we mapped the red spruce extent, as well as other land covers such as deciduous forest, grass, soil, urban, and water. Landsat 5 went up in 1984 and was in service until 2012, actually long extending past its original life plan. So it was a really great satellite. It provides information in 6 multispectral bands, 3 visible bands of the red, green, and blue, as well as a near-infrared and 2 shortwave infrared. A great thing about these near-infrared and shortwave infrared bands is that they see things that the naked eye can't see. So they really are crucial for like assessing vegetative health, vegetative abundance, identification, and so much more. Landsat 8 was launched in 2013, and we used that for our 2018 image. Landsat 8 tends to match Landsat 5 in its spectral bands, although it does have 2 extra multispectral bands in the cirrus cloud and aerosol bands. We did not use either. Both satellites that are Landsat have thermal bands as well, which we also did not use. Landsat offers a spatial resolution fairly fine for what is given away for free. It's 30-meter resolution, so about a 900 square meter pixel. And it has a revisit time of every 16 days. So it's a really standardized data acquisition for every area. So every area on Earth gets a revisit of 16 days and an image is taken, with the only limitation really being if there's cloud cover. If it's a clear sky, you get a really great image, and they're very useful, and they were very useful to us. Lastly, we also used the Shuttle Radar Topography Mission, which was a 2000 mission in the year 2000 that mapped elevation around the globe. And we used this for using as our digital elevation model. We also did some elevation derivative products of slope and aspect with this SRTM data. With all that data, we kind of used a host of software, both open source and private. Google Earth Engine we used as image acquisition and training data collection. It's a JavaScript-enabled tool. Excelis NV 5.5, which is part of the Harris Corporation. We use that for some data processing, generation of some image derivatives, and we also stacked some layers in it. ArcGIS 10.7 in ArcMap, and as well as ArcPro, we did some data visualization. as well as our habitat suitability model, which Tia will talk about later. And then TerrSet Adrisi, a really great raster processing software that's out of Clark Labs in Massachusetts. This actually, we did a lot of our data processing as well as image derivatives. And our classification tree analysis for image classification for our 4 years, as well as land cover change forecasting in the Land Change Modeler wizard that comes in Adrisi.
So in addition to the NASA Earth observations that Jake mentioned, we also had a bunch of really helpful data provided by our partners, including shape files of the boundaries of both the entire Monongahela National Forest and our specific study area, Sharp's Knob. We also got validation points that told us where exactly red spruce are located, and this was really crucial in training our model, which I'll talk about in just a minute. We also got forest cover polygons, which was, again, helpful in classifying the forest, and really high-resolution aerial imagery that allowed us to collect the rest of our training data. And so now you're actually looking at a snippet of that high-resolution imagery. And so what we did, the first step in terms of classifying the forest is to collect points and kind of teach the computer how to find land cover and tell us where red spruce is located. So in this image, you're seeing 1 as red spruce, 2 is deciduous, 3 is grass, 4 exposed soil, 5 water, and 6 urban and impervious surfaces. And so by collecting over 1,000 points per year, we were able to train the model and get some pretty robust classifications using both a leaf on and a leaf off image, because helpfully the conifers don't lose their needles, but the deciduous trees do lose their leaves.
So then, taking all of this data that we'd had and all of these images that we had, we were able to create a classification of the entire forest. So using the Landsat imagery we had, we generated some image derivatives such as NDVI and NDMI, which respectively are the normalized difference vegetation index and normalized difference moisture index, which help us look at vegetation density and vegetation health. And then we also use the multispectral bands from the blue band to the shortwave infrared 2 band in Landsat 5 and 8. And then using the SRTM data, we were able to generate slope, aspect, and elevation of the entire forest. And then using what's called a classification tree analysis in TerrSet, we were able to classify the entire forest into these 6 classes that we talked about on the last slide. So you can see the red spruce, deciduous, grass, soil, water, and urban, using those training sites that we collected in Google Earth Engine, and as well as some other using that aerial imagery. And then we were able to take this and dump it into a time series analysis in Adrisi TerrSet. So we had the classifications from 1989, 2001, 2007, and 2018. And taking all of these images, we put them into the Land Change Modeler, and it forecasted us out to 2040. So there you can see in that image, there's some persistent red spruce, there's some change to red spruce on the periphery of that, and then just some other change that we weren't too concerned about in the Monongahela.
All right, so now that we know where red spruce is, was, and could be, we wanted to use this information to find out where suitable habitats are for red spruce within the Monongahela and within Sharp's Knob. And to do this, we used a fuzzy logic model. To put it simply, a fuzzy logic model, what it does is it takes the raw values of all of our data inputs and it transforms it into a spectrum that ranges from 0 to 1. Values of 1 are considered pixels that are 100% suitable for red spruce, whereas values of 0 are considered pixels that are absolutely not suitable for red spruce. And using the spectrum allows us to sort of capture the uncertainty that is inherent with habitat suitability modeling. Now, to get a little bit more into the nitty-gritty details of fuzzy logic, you break it down into 3 steps. And the most important of those steps is assigning what's called a membership class to all of our data inputs. So take an example, elevation. We used a linear relationship to describe elevation. Now that may not make sense at first because obviously elevation isn't linear. But a linear relationship actually describes the relationship between red spruce and elevation pretty well. As I'm sure all of you on this call are very well aware, red spruce tends to prefer elevations that are above 900 meters. But once you get above that 900-meter threshold, red spruce doesn't really tend to prefer any higher elevation. So for example, you're not more likely to find red spruce at an elevation site that's at 1,400 meters compared to a site that's 1,000 meters. So in order to model this relationship, what we did was we assigned a linear membership class to our elevation data inputs, and we gave it a maximum value of 950 meters and a minimum value of 850 meters. And what this does is it tells our toolbox to assign any raw elevation values that are above 950 meters a value of 1, or absolutely suitable for red spruce, and any data values less than 150 meters a value of 0, or absolutely not suitable for red spruce. And in between that 850 to 950 meter range, it then linearly increased from 0 to 1 using all of that information. In addition to the linear membership class, we used 2 other membership classes for all of our data inputs. We also used a large membership class, and all that means is that larger raw data values are more likely to be suitable for red spruce. So for example, we used this equation for our frost days because red spruce tend to prefer areas that have a higher number of frost days. We also used a small membership class, which is essentially the inverse of that large membership class. It just means small data values are more likely to have high suitability. So we use this for our growing degree days input. And then, so as you guys can see, our inputs included topographic derivatives, climate data. We also included some soil data, and then distance from roads.
All right, and then with all of those great methodologies, we ended up getting some really, really great results. This is a time series analysis, basically of our land cover classification from 89 to 18. We were able to achieve a relatively high classification accuracy, around 80 to 85% for all 4 years, consistent with what the literature considers very good for remote sensing, particularly with 30-meter resolution. Over the entire Monongahela National Forest, during the 30-year time period, we saw a 13% increase in red spruce, or just shy of 18,000 hectares. Within Sharp's Knob, we saw an 8% increase in red spruce extent, or just under 250 hectares. Interestingly enough, though, the trajectory of this like regrowth or increase in red spruce did not happen like at the lowest point being the beginning of our time period and the highest being at the end. We actually saw a deterioration of red spruce both in the entire Monongahela National Forest and Sharp's Knob between 1989 and 2001. In the 17 years between 01 and 2018, we saw a restoration of red spruce that actually exceeded what it was prior to 2001.
So next, using all of that data, we were able to generate a forecast model from 2018 to 2040 in Adrisi TerrSet. This model kind of showed that 11% of deciduous forests throughout the Monongahela are expected to fall out of deciduous and come into red spruce, as well as around 4% of all soil, exposed soil. So you can see there in the image on the right that that pink is that spruce that's persistent from 2018 to 2040, and then that deep red on the periphery is what's kind of changing to red spruce. So there's not a lot of change, but there is some, which is good news.
And after executing our habitat suitability model, we were able to determine what areas within Sharp's Knob are highly suitable for red spruce. So in the map on the right of your screen, those dark green areas, those are very high suitability areas, and those light green areas are high suitability areas. Then in order to really understand how these areas intersect with current red spruce extent, we added a data layer that was extracted from our classification model. All of those areas that were classified as red spruce, we extracted that and then added that to this map in the gray on the screen. And doing this, we determined that 1,040 hectares are suitable for future restoration projects. And we got to this number by determining the number of hectares that are not classified as red spruce or are not in gray on that map by our CTA model, but are still considered very high or high suitability by our fuzzy logic model.
And with over 1,000 hectares capable of high suitability red spruce habitat, it would be great to restore all of it. But I'm sure, as you all know, that time, resources, and accessibility are all limitations to where red spruce can be restored. So knowing the optimal areas to restore red spruce, to maybe create larger stands of red spruce, is a priority. We were able to use a really great tool in ArcGIS called Linkage Mapper, which is a plugin that you can download. And basically, it mapped areas' highest connectivity potential. The inputs into determining what had the highest connectivity potential was where the red spruce currently exists, which we called our spruce core, and then it took the Euclidean distance between where red spruce currently exists. In the distance between red spruce currently exists, it also took into account how suitable that area is. So if two red spruce stands were very close together, it might not be the most highest potential for connectivity because the land in between the red spruce might not be as suitable as areas where maybe the gap was broader. In the map, you can see purple represents the highest area of connectivity potential. And within the Monongahela National Forest, it is a mixed bag. There are areas where you can restore, and there are areas where there's a low prioritizing connectivity. However, within Sharp's Knob, a majority of it has very high connectivity potential, which I know for the red spruce restoration is exciting news.
So hopefully throughout this presentation, we've conveyed that you can successfully use medium resolution multispectral imagery such as Landsat to classify and identify red spruce stands, particularly in the Monongahela National Forest. According to our forecast model, the trends of land use and land cover in the forest over the past 30 years are not sufficient to reclaim the historical extent of red spruce stands by 2040. The good news is that within Sharp's Knob, nearly all areas are suitable for restoration. And so those initiatives put out by the USFS are really going to make a difference. Thank you so much for coming. These are the people that we would like to thank. We couldn't have done it without them. It definitely wasn't just us four. It was our partners, our science advisor, our center lead. We really, really appreciate everything that everyone has done for us. Are there any questions?
No, folks, if you have questions and you're on the line, feel free to unmute yourself unless we have to do it on our side. Unmute yourself and then ask away.
So this is Sam Lammy, and great presentation. The project, I really like everything that you did. One question I have, I thought it was very interesting. You mentioned it sounded like there was a decline before 2001 of red spruce.
Yeah, our model showed between 1989 and 2001, both within Sharp's Knob and the entire Monongahela National Forest, our model, in our classification model, showed a decline in red spruce extent in those 12 years. Granted, we did have 84% accuracy, so there might be some inconsistencies with that, but the decline was large enough that we think the imagery showed at least some decline.
Huh, interesting. Yeah, appreciate that. And then the other, let's see, I had another question. I'll come back to it. Maybe see if someone else has a question.
No worries.
Yeah, thank you.
Well, while you're thinking, Sam, or while others are waiting, I suppose, we'd like to let you know that the deliverables will be delivered. Very soon. What we're going to do is kind of package those things up. I'm going to put it on one of my servers here, and then you will receive an email with a URL to download that zip file, and you'll have all the deliverables. And we're ready to make that delivery by the end of this week, right?
Yeah, absolutely.
Okay.
Yeah.
Yeah, that sounds super. Hey, appreciate it.
Hi, this is Katie Barlow with TNC. Thanks for the presentation. It's really great to see this research coming along. I was curious if you, and maybe I missed it in the beginning, but were you able to distinguish between a red spruce dominated forest and a non-native pine plantation?
For our land cover classification, we just did red spruce as the only conifer tree. There are other coniferous trees in the Monongahela National Forest. I think from our understanding, though, the overwhelming dominance was still red spruce. But I think What else did we see? Is it hemlock? Is that one of the?
Hemlock would be there as well. So you were able to zoom in close enough to see the difference? Is there a spectral difference between red spruce and, say, a non-native pine plantation?
So with the 30 by 30 meter pixels, it's pretty tough to get in that far and see. Even with the high res imagery that we had from our partners, it was pretty hard to tell the difference. But we were working under some assumptions that red spruce existed pretty much everywhere in the sub canopy, as well as what we could see in the overstory. And so working with that assumption, we just assumed that if we saw a pine, it was red spruce, especially if it fit that suitability analysis.
Okay, so there could be a little bit of error in that the model could be pointing to places where pine is expanding versus red spruce is expanding.
Yes.
Yep.
Yes, absolutely.
Yep, absolutely.
Any recommendations on that in the future as our partners use this type of modeling to plan for?
Oh.
Normally what you're going to need to do on something like that is get a satellite sensor that has a small enough spatial resolution so that essentially you'll have that pixel or all the pixels covered homogeneously by one tree or one type of tree. Once you have that, that makes things a whole lot easier to then start teasing out the slight spectral differences between red pine, red spruce, hemlock, and so on and so forth. But with a 30 meter by 30 meter resolution, such as on Landsat, and the training site's being set for red spruce, when it classifies that this pixel is red spruce, what it's saying is that to the best of its ability, that is red spruce. Is it 100% red spruce? No, probably not. Is it mixed in with red pine? Could be. Is it 100% red pine? Maybe. It could be. But I think that with the source data that we were using, or the team was using, that's about as deep as we can get, or as finely resolved as we can get at this point.
Okay, thank you.
There's also, there is, like Keith mentioned, there's higher resolutions on the spatial scale would be like magnificent. There is a European Space Agency satellite called Sentinel, which offers higher spatial resolution than Landsat, possibly not high enough to still distinguish. Another thing you can do in addition to what Keith said is there's a thing called multiple end-member spectral mixture analysis, where you would take a pure pixel or like a plantation pixel of like this red spruce and hemlock and other types of conifer trees, and you run an algorithm on it, and it'll basically take the larger pixel, and it can't give you configuration within that pixel, but can give you composition. So the output would be this 900 square meter pixel is 17% red spruce, 17% hemlock, and then 66% deciduous tree. The software to run that is a little bit more complicated, but it certainly is doable, but as well with varying results in its accuracy and integrity.
Okay, thank you.
This is Sam again. I remembered my question. So you forecasted out to 2040, and what data did you use to do the forecasting in terms of the climate?
So the climate data that we gathered, it was MACA data, which I unfortunately can't remember what the acronym stands for right now.
It's I can give it a shot. It's multivariate analogous, constructed algorithm, which is a downscaling of a 20 global climate mean. So basically it takes every 20 global climate models that has a projection, and it basically downscales it to a resolution of 1.4 kilometers. And it's a mean of these forecasted climate models for a 30-year window based on business as usual carbon projections, like how much carbon we're releasing into the atmosphere, known as RCP 4.5 and RCP 8.5. 8.5 would be business as usual. RCP 4.5 would be that we implement some policies that would restrict like carbon fuel burning and stuff like that?
In general, for our land change modeler, in addition with the business as usual climate data, our model in general was business as usual. So we input, I believe, distance from roads, elevation, aspect, and slope. Those were our inputs. So we didn't really play with different management scenarios. It's more of if you keep doing what was done from 1989 to 2018, here's a forecast for 2040.
And
Sure.
that being said, it could be understating the increase in red spruce or other conifers because of that dip that we saw from 1989 to 2001. That kind of suggests to me that the trend is being that has increased in the past 17 years.
I guess, you know, I noticed you use frost days, and it's a large impact. I wonder how much difference there might be if those frost days, there was quite, or relating to growing degree days, change disproportionately, I guess.
Yeah, so the idea, what you're saying, Sam, if I'm understanding this, is to model a warming climate, thereby to simulate that inside a Picea would reduce the frost days and increase your growing degree days. Is that right, Sam?
Yeah, yep, yep.
To do that, right? We did the business as usual.
Yeah.
Now, your workflow tutorial, does it talk about those steps? The person can start gaming, if you want to call that gaming with it? Trying different.
Within the tutorial, it does show you where you can download different scenarios of in climate windows.
So that variable came in with that composite climate.
Yep.
set?
Yeah, so the MACA data, when you download it, you can download three types of the data for things like growing degree days, frost days, precipitation, temperature, and they're historical from 1971 to 2000, and then a forecast from mid-century and late century. Yeah, and so you can download those three different things. We just did the forecast with business as usual carbon output, and that was what we used. But you could definitely add in those different data to see what's changing where and how.
Just replacing the
data.
Yeah. And also with the spatial resolution of these climate data, they're even more coarser than the Landsat pixels. So the variation that could be experienced within like Sharp's knob is not going to be captured super well because the spatial resolution is so coarse.
Sure.
Also, with forecasting red spruce, also with forecasting up to 2040, even with different climactic scenarios, the red spruce lifespan, if you will, is so long. Even with different climactic scenarios, we might actually not see that much decline from now to 2040, just because we don't know if climate change is going to affect seedlings, and that's how you see red spruce decline, or if it's going to affect existing stands. So even with adding a not business as usual climate model to this, we may not actually see a lot of decline up to 2040 without understanding what stage climate change affects with red spruce propagation.
Sure. No, hey, appreciate it. Thanks.
And of course, 2040 sounds like it's a long ways out, but we're just 2 decades out.
Yeah.
Right.
Yeah.
We're not that far out. Are there any comments on the or questions specifically about the restoration areas, the projected or restoration areas, high suitability, the linkages, and those sort of things?
Hi, this is Patricia. I have a question about that actually, and I know that the Monongahela has been doing quite a bit of restoration of former mitigated mine sites, doing deep ripping of soils and things like that. And so did you distinguish at all between areas that were already functioning ecologically versus areas that were currently being restored versus areas that, were really in arrested succession and not likely to expand on the landscape without, some pretty intensive management?
So honestly, with our habitat suitability, we really didn't input any of those more ecological variables, such as, like you were saying, succession. Is it a former mine site? Is it currently being restored? We did a lot more sort of environmental factors, such as topography. We did soil data, such as soil pH and percent silt, percent sand. And then finally, we also did that climate data, like growing degree days, frost days. So we really didn't integrate sort of that, that management scenarios. But I do think that could be a really interesting expansion of our habitat suitability model. But no, for this stage, we did not include that.
Okay, thanks. And I'm sure that the managers know where those places are and can kind of do their own level of, oh, that makes sense versus, that's really not going to work there.
Yeah, Kristen here, and kind of just listening to it, you guys did an amazing job in 10 weeks, and I can definitely see it being kind of tweaked and tinkered with as we go along, and it seems like a very valuable start. So just wanted to say that.
Thanks, you.
Kristen.
Thank you. I agree. I think that there's a lot of opportunity for future work on this. Unfortunately, 10 weeks flies by in the blink of an eye. And the analysis we were able to do was, I think, a good benchmark, but I really do feel that maybe introducing like a higher resolution satellite like Sentinel, or like messing around with the different climate scenarios. And as you, Patricia, just said, maybe distinguishing hey, this is functioning as like a grassy field versus an area that maybe has grass reclaiming a former mine would be functionally different in potential, but we treated them as equals. But distinguishing those two, I think, would add a lot of integrity to the model and maybe its outputs.
This is Amy on the Monongahela, and no question at this time, but I did want to give a big thank you to the whole NASA Develop team. I'm very excited with what you guys have produced for us, and I'm ready to get out in Sharp's Knob and put this into action. So thank you for all that you've done, and as I've said many times before, we invite you to the Monongahela to visit the area and actually help us with some of this restoration work.
No, thank you so much, Amy, Sam, Stephanie, I know isn't here, but you guys and everyone at the Monongahela National Forest has really been great project partners. I've been involved with a couple develop teams, and you guys have really been great and keeping up with, giving us the data maybe we requested, and if you can't get the data we requested, offering hey, would maybe this alternative work? So we really appreciate that. We know you guys are all very busy, and this was just another thing to throw on you guys, but we just really appreciate it.
Great. Thank you guys again.
Yeah, that's okay. You can throw things like this on us anytime.
These are the projects we enjoy for sure.
Yeah, definitely. And actually the connectivity, the part of the effort to look at connectivity, I think with Amy, I mean, that really is, for anybody that's halfway curious, I think that has a lot of potential. So, we'll be looking to getting your deliverables and digging in a little bit deeper. So thanks again.
Yeah, absolutely. The linkage part of it was something I really enjoyed doing. We didn't get to dig as deep as we would have liked to. The toolbox that we were able to use, Linkage Mapper, has additional tools that will even make connectivity networks. So future work, and we'll provide that in the tutorial, the resources on where to access this information, but you can actually even take it a step further than we did, which maybe would be of interest to you, maybe not, but it's almost from a landscape ecology perspective, what type of corridor can be created versus just like connecting extent. But yeah.
I'll just hop in here too. We had a great time working with you guys also. So keep us in mind. We have 12 different offices across the country, and we're always looking for projects that can help build the capacity of our participants and help put these different tools in the hands of our partners. So I'll be sending out kind of contact information along with the handoff, and feel free to reach out if other things come up in the future. We really enjoyed partnering with you.